Hi guys, welcome back to another video. Today we're going to be discussing 2026 IMO Problem 2. This is a nice geometry problem that appeared on the IMO a week ago. So without further ado, here's the problem. Let ABC be a triangle and let points M and N be the midpoints of sides AB and AC respectively. Let points K and L be chosen strictly inside the triangles BMC and BNC respectively, such that K lies strictly inside triangle ABL and L lies strictly inside triangle AKC. Suppose that angle KBA equals angle ACL, angle LBK equals angle LNC, and angle LCK equals angle BMK. Let O be the circumcenter of triangle AKL. Prove that the lengths OM and ON are equal. Okay, so what do we do first? Well, what we do in any geometry problem first is draw a diagram. So let's go ahead and draw a diagram. So suppose we have our triangle ABC. So we have A, B, and C. Then we have points K and L chosen inside the triangles BMC and BNC. So M here is the midpoint of AB, and N is the midpoint of side AC. So it seems like the triangles BMC and BNC are not too relevant for now, so let's worry about them later. It seems like that's only to make the problem nicer in a way. Anyway, so suppose we have K and L, and can have K and L here, such that angle KBA equals angle ACL. So that means that if I draw this one here and this one here, then that means that these two angles are equal. And then angle LBK is equal to angle LNC. So LNC. So that means that these two angles here are equal. And these don't look too equal in our diagram because we basically just guessed where the points K and L are. In general, when we don't have much information, like we don't in this problem, about how to construct the points K and L, we can't really do much. And then we also have LCK is equal to BMK. And then we have these two here. And I'm going to go ahead and mark those angles in green. Anyway, we have these 2 points K and L that satisfy all these weird angle conditions. And then we have one final point to add. We draw in the circumcircle of the triangle, so something like this, and let O be a center. And what the problem asks us to prove is that OM is equal to ON. All right, so how do we get started on this problem? Well, the circumcenter feels very, very arbitrary, so let's go ahead and ignore it for now, actually. And let's go ahead and ignore that circle as well. Let's try finding out as much information about K and L as we can. Because in general, we don't want to get too ahead of ourselves and just start worrying about the point O immediately. It feels like the point O will come later in our proof. But for now, let's just worry about finding more info about points K and L. Because first of all, we don't even know how to construct the points. And if we don't know how to construct the points, well, there's not much we can really learn about them anyways. So let's first see. So we first have angle KBA equals angle ACL. So in other words, these two angles are equal. So this really looks like, because we have this one here is equal to this one here, it really reminds us of the cyclic quadrilateral property, that when you have a cyclic quadrilateral here, then we have that this angle here is equal to this angle here. So how can we really form a cyclic quadrilateral with the K and L? Well, because we want this side here to be this one here, AB, and this diagonal line to be BK, and it intersects the line AC here, it really makes sense to look at the line BK intersect AC, the point. And I'm going to go ahead and call this Y, no X. And then I'm going to call this one Y. Then what we know about this here, about these points X and Y, is that because these two angles here are equal, the two red ones, this tells us that BXYC is cyclic. All right, so now let's move on to the green angles. What do the green angles tell us? Well, because we know that these two angles here are equal, they are the green angles. We want to relate them to the points y and x somehow. So we know that this angle here is equal to angle YCK. So that's one thing. How can we relate BMK to y or x? Well, we know that y lies on the line AB, so we want to incorporate that somehow. After all, the only other info we know about y, other than BYXC being cyclic, is that y lies on the line AB. So that means that angle BMK is actually equal to 180. So let me write it down. BMK equals 180 degrees minus angle YMK. And we know that this is also equal to angle YCK. But look, that means that angle YMK plus angle YCK is equal to 180 degrees. In other words, if I mark this angle here in purple, then the purple angle plus the green angle is equal to 180 degrees. And therefore, that means that let me go ahead and erase this. That means that YMKC is cyclic. And if we repeat the same thing for the blue angles, we know that the blue angle here plus, let's say, the yellow angle here is equal to 180 degrees. And this means that B, X, and L is cyclic. All right, so now we have all of these three cyclic quadrilaterals. Let's see what we can do. Now let's see what we can do with the cyclic quadrilaterals. But wait, you may ask, what happened to the diagram? And this leads me to another point I want to make about this problem. Now we know about the problem that we found some cyclic quadrilaterals, we can actually try to reconstruct the diagram. And this is an important philosophy in geometry. If you can't construct a diagram immediately, as you find out more information about the points in the problem, you're going to be able to construct the diagram better and better. And hopefully by the end of the problem, by the time you solved it, you'll be able to construct a completely accurate diagram. Anyhow, let's go ahead and reconstruct our diagram with this info. So we have our triangle ABC. So that's obviously the first thing we draw. So A, B, and C. And then we have point M and N are the midpoint of AB and AC. Then we have the point K and L, and they satisfy these weird angle conditions. However, we reduce these angle conditions to a bunch of quadrilaterals being cyclic. So we first start off with BYXC being cyclic. And this motivates constructing the points X and Y first. So X can be somewhere here, and Y can be somewhere here, such that this quadrilateral here is cyclic. Sorry if that's a bad circle. And then we have that BNXL is cyclic. So let's go ahead and draw in the circle BNX. So BNX looks something like this. But the fact that X lies on BNX is not enough information on its own. So what else do we know about L? Well, we know that L lies on CY by definition. Otherwise, how do we even get this point Y? So that suggests that, let me go ahead and move this point Y, this label Y here somewhere else. So here is a circle again. Then if this point, I'll label it Y like over here. Then if we construct this line here, CY, then we should get the point L. And similarly, if we construct the circumcircle of YMC and intersect it with BX, we should end up getting the point K. So let me do that in blue. So we have this circumcircle here. And I'm not going to draw the full one. And then we intersect it with BX. and that should give K. And now we have the points K and L as we need. But you might have noticed something about this diagram. Well, we know that L lies on CY and B and X. But even though we know that L lies inside the triangle, and inside the triangle B and C specifically, this actually doesn't really say much because the B and C condition, as I said earlier, seems to just make the problem nicer, so to say. So in reality, it seems like this other point out here, which I'm going to call L prime, should also satisfy the problem condition. In other words, if I change the point L to the point L prime, then basically no one should notice. Like the problem does not notice at all. In other words, this means that the circumcircle of AKL prime should have its circumcenter lie on the perpendicular bisector of MN. So that means that the circumcenter of AL prime K has MO equals ON. And similarly, if we construct this point K prime up here, I'm not gonna, it may be hard to do this because it will overlap with the problem statement. So I'll call this K prime here. Then that means that the points K and K prime are also equivalent, which means that the circumcircle of ALK prime should also satisfy MO equals ON. So we have a bunch of perpendicular bisectors of all of these related points, satisfying a weird condition about the perpendicular bisectors and the circumcenter. So the circumcenter of AL prime K lies on this perpendicular bisector. The circumcenter of AL prime K prime lies on the perpendicular bisector. The circumcenter of ALK prime lies on the perpendicular bisector. And of course, we want to prove that AKL has a circumcenter on the perpendicular bisector as well. And again, all these statements we don't know are true yet. We're trying to prove them. But based on what the problem statement asserts, it feels like all these statements would be true for the other points as well. So we have 4 circumcenters lying on this perpendicular bisector. So what's a nice way for that to happen? Well, if they're just all the same center. So in other words, we really want all these 5 points to be concyclic. And I'm going to go ahead and draw this circle really weirdly here, which means that we drew a bad diagram. But this doesn't really matter because we have this point K prime is all the way out here, and we could probably draw a better diagram later. All right, so now that we know that we want to prove that A, K, L, K prime, L prime are concyclic, that's one of the main goals. Because that seems to align the best with OM equals ON. So let's see if we can prove something simpler. So let's go ahead and construct this intersection point Q. Can we prove that KL, K prime, L prime is cyclic? Well, let's see. We can try using power of a point at Q because we know a lot about the lines BX and CY. In general, if we know a lot about the lines that the points lie on, it's a generally good idea to use power of a point because we don't know much about the angles themselves. Anyways, let's use power of a point. So we have L prime Q times QL, or should I say, I'll go ahead and write it as QL prime times QL. What is this equal to? Well, if we look at the definitions of L prime and L, we note that this is just the points on this red circle. So let's use power of a point on this red circle. Then this becomes QX times QB. Okay, so now we have this point Q where we use power of a point on the red circle. Now what about the blue circle? This becomes QK times QK prime because the K and K prime lie in the blue circle. This is equal to QY times QC. So therefore we want to prove that these two are equal. In other words, QB times QX equals QY times QC. But if you notice, because we're using power of a point, it makes sense to try using power of a point to prove this. And then we realize that BXYC is cyclic. So that means that this is just true by power of a point. All right. So now we know that KL, K prime, L prime is cyclic. So we want to understand more about its center, the circumcenter of KL, K prime, L prime. Okay, so I redrew the diagram, and now hopefully the points K prime and L prime are a bit more accurate now. So anyways, we know that KL, K prime, L prime is cyclic, and we want to figure out more about its circumcenter. So let's see what we know about points L and L prime. So first of all, we know that they lie on the line CY. So we ideally want a line perpendicular to CY. And moreover, we know that L prime and L both lie on the red circle. So that means that their perpendicular bisector should be something related to the circle because after all, it goes through the center. So let's try figuring out more about this circle. Well, we know that if we try intersecting the circle again with the side AB at this point here, then I'll go ahead and call it, suppose, I'm going to call it N prime. And you'll see why in a bit, because if we use power of a point at A, which makes sense because we're intersecting with line AB, then we get AN prime times AB. What is this equal to? Well, if we use power of a point on the red circle, this becomes AX times AN. But we still haven't really used the fact that N is the midpoint of BC. And then when we do this, this becomes like 1/2 AX times AC. But we can try using power of a point at A again. And doing so, we get 1/2 AY times AB. And now note that these ABs cancel out. And so AN prime is equal to 1/2 AY. In other words, N prime is a midpoint of AY. And similarly, we get that this other point here, which I'll call M prime, is the midpoint of AX, which is why I call them M prime and N prime. Okay, so now we have that M prime and N prime lie on these circles. Let's see how they relate to the rest of the points. Again, we want to use the fact that N is the midpoint of AC, because we haven't really used that much yet. And then one thing that we notice is that because we have these midpoints here, we're motivated to try connecting them together. And this actually means that N prime N is parallel to CY. And if you're wondering how you come up with this, it's just because you have these midpoints here. It's a really hard observation to make, and I may have just skimmed through it a lot, but just note that because you have these midpoints here, you want to relate them somehow, I guess. Anyhow, now we have that N prime N is parallel to CY. We know that it's also parallel to L prime L because, well, the only really definition of L prime and L is that they lie on CY and the red circle. So so that means that they are also parallel to L prime L. And this means that this quadrilateral here, because all these points lie on the circle, it's an isosceles trapezoid. So N prime N L L prime is isosceles. But what exactly does this mean about the perpendicular bisector of L prime L? Well, it just means that N prime N and L prime L share a perpendicular bisector. And that means that I'll go ahead and draw on this line here. This is our perpendicular bisector. And similarly, the perpendicular bisector of KK prime is the perpendicular bisector of MM prime. So something like that. So the intersection of these two perpendicular bisectors is our desired circumcenter. So the intersection of the perpendicular bisectors of MM prime and NN prime, and we want it show that this point, which we know is O now, must lie on the perpendicular bisector of MN. So it must be this as well. So 3 perpendicular bisectors among these 4 points concur. They meet at the same point, which should mean that M prime N M N is cyclic. So in other words, we want to see if M N prime M prime N is cyclic. So this could be cyclic. And because we have all these midpoints, the midpoint of AY, the midpoint of AX, the midpoint of AB, and the midpoint of AC, and all these midpoints involve the point A, we want to try taking a homothency of scale 2 at A. Then this point N prime, as I said earlier, becomes Y, this becomes X, this becomes B, this becomes C. Hey, wait, because BYXC is cyclic, this means that MN prime N is also cyclic. So therefore, that means that the circumcenter of KL K prime L satisfies the MO equals ON as we need, because it lies on the perpendicular bisector of MN, because it's the center of the circle MN prime M prime N. But does this mean we're done? Absolutely not. Because recall we haven't even shown that A lies on this circle here. But the fact that the circumcenter should be the circumcenter of MN M prime N prime tells us a lot of information. Okay, so I've added in the circumcircle of MN M prime N prime, and we're going to redefine this to be the point O. Then we want to show that this point O here, because we know that it satisfies MO equals ON, we want to show that A lies on the circle KL K prime L prime as well. And based on the homothency that I suggested earlier, the idea of drawing in the circumcircle of BYXC and labeling its center as well is also motivated, because we just take a homothency of scale 2 of the maroon circle. So I'm going to go ahead and highlight the circle in a darker purple color so that you can see it more, because it seems like we're going to be centered around the circle. So we have O prime here. That's the center of our pink circle. And we note that O prime is the reflection of A across O by homothency. So that means that if O were actually the circumcenter of the triangle AKL, which is what we need, and what we hope to be the case, then if we reflect A across the center, well, we just get the point that's diametrically opposite the point A. So if we look at this point here, O prime, that means that, let me go ahead and draw it in a different color. We know that angle AKO prime should be equal to 90 degrees. And so should the line angle ALO prime, but the diagram is slightly bad. So we'll focus on AKO prime for our purposes. So how do we exactly prove that AKO prime is 90 degrees? Well, we also know that angle ALO prime is 90 degrees. So by this symmetry, this should also mean, and again, the diagram is slightly bad, that AK prime O is 90 degrees, and then angle ALO prime is 90 degrees. So really, it seems like this circumcircle of KL K prime L prime is just a circle with diameter O prime. So I'm going to go ahead and draw this in. And it's not going to have, it's going to very barely have L and K, but this is what it is for our purposes. So we want to show that the yellow circle here has the points L and L prime on it. Well, what if it did have the points L and L prime on it, or K and K prime? If it had L and L prime, that would mean that the line L prime L is the radical axis of the two circles. And this is basically equivalent to proving that the points intersect at L and L prime. Because if we prove that the radical axis of the yellow circle and the red circle is equal to CY, that means that it must also be L and L prime, and those must be the two intersections. So this radical axis fact should be true. And similarly, Bx should be the radical axis of the yellow circle and the blue circle. So how do we prove that a line is a radical axis? Well, we just want to prove that the power of c with respect to the yellow circle is the same as the power of c with respect to the red circle. First, let's calculate the power of c with respect to the red circle. This power is just equal to, because we have the segment AC here, and it's easy to deal with that in terms of the line AC, it's Cn times Cx. And because Cn is half of AC, this is equal to 1/2 Ca times Cx. Now we want to find the power of C with respect to the yellow circle, which is a circle with diameter AO prime, as we said here. Based on this logic, we want to find the power of C by using line AC again, because it seems like we can get away with lengths. So let's go ahead and intersect this side here with the other side, so that's Z. Then what we really want is for it to be equal to Ca times Cz. In other words, for Cx over 2, so Cx over 2 to be Cz. In other words, the midpoint of Cx should be the point Z. So how do we prove that the midpoint of Cx is Z? Well, the only thing we know about Z is that the angle AZO prime is equal to 90 degrees because it lies on the circle with diameter AO prime. And this means that XZO prime is 90 degrees as well. But wait, because O prime is the center of our circle, this means that Z should already be the midpoint by, say, congruent triangles. Because we can draw this in, and then this should be the right angle here. Okay, so now that we know that Z is the midpoint, that means that C lies on the radical axis. So of course, this begs the question, does Y lie on the radical axis? Well, let's figure out the power of Y with respect to the red circle. This red circle is slightly hard to see because it's one of the first circles we drew in the diagram, but the power of Y is equal to Y, then this other point here is N prime, and here we're using the segment AB because that's how we relate Y to the other sides. So anyway, we have Yn prime times Yb is equal to the power of Y with respect to the circle of B and X. And when we use the fact that N prime is the midpoint of AY, recall this from earlier, and you can tell from this diagram by the tick marks, this is equal to 1/2 of YB times YA. So if we can show that this is the power of Y with respect to the yellow circle as well, this would be amazing. And the power of Y with respect to the yellow circle is equal to it should be AY times, and then if we let this intersect at a point W, sorry if that's hard to see, then it's equal to AY times AW. Then these guys cancel out here. So we want, this should be YW and YA. So that means that we want YW equal 1/2 YB. So in other words, W is again the midpoint of YB, just like how Z is the midpoint of XC. And therefore, this is already true based on our discussion about Z. Because W is the midpoint of Bn prime, or based on what we're assuming, if angle AWO prime is 90 degrees, that forces W to be the midpoint. So W is the midpoint because we have this circle with diameter AO prime. Thus, by power of a point, C and Y lie on the radical axis of the red circle here and the yellow circle here, which means that the radical axis is indeed L and LL prime. So that means that L lies on the circle with diameter AO prime, the yellow circle. And so does the point K. Therefore, the point O prime is the point diametrically opposite A across the triangle AKL. And finally, the midpoint of AO prime is also the center of the yellow circle. And when we take the midpoint of AO prime, we get this point O here. And we want to prove that MO equals ON. But now we can try taking a homoscedity of scale to A to bring M to B and N to C. Then O goes to the point O prime. So really what we need to prove is BO prime equals O prime C. But wait, this is just true because if we look at the purple circle here, these two are equal to the radius of the purple circle. And therefore, this means that BO prime equals O prime C, and this finishes the problem. In fact, if you're observant, you might have noticed that the points K prime and L prime were actually not used in the proof really at all. And indeed, let's see an argument that does not use the points K prime and L prime. That's just very similar to what we did. So as we did in the first step, we first intersect BK and CL with the opposite sides, and these give the points Y and X. And here, Y and X are just close to M and N for some reason, but okay. So now we know that we have Y and X here, which means that BLXN is cyclic. So BLXN is cyclic, and so is this circle here. This is also cyclic. And I should draw it like this to avoid any confusion. So sorry if this is a bad circle, by the way. Anyhow, because these two quadrilaterals are cyclic, that means that we can draw in the midpoints of X and AY, which I'll call M prime and N prime. By power of a point at A, you can end up showing that these points actually lie on these two circles here. And therefore, we have N prime and M prime here. Now, let's go ahead and construct the circumcenter of BXYC. So let's go ahead and do this. And this is the center O prime. Then what we're going to be doing is I'm going to go ahead and erase this and go ahead and draw on this O prime here. Then we're going to be showing that the power of C with respect to AO prime is also the power of C with respect to BNX here. And similarly for the point Y. This will show that CY is the radical axis of the two circles. And because L lies on the one circle, it must lie on the other, meaning that ALO prime equals 90 degrees. And then similarly, angle AKO prime is 90 degrees, and this means that the center must lie on the perpendicular bisector of MN by homoscedity. And to find the power of C with respect to this circle here, we just use power of a point again. If we intersect this side here at a point Z, then Z is the midpoint of CX because it's the right angle here. And that means that the power of C with respect to the red circle and BNX is the same. And you can do something similar for the point Y by letting this midpoint here be W, which lies on the circle, and then using power of a point at Y using the midpoints. And therefore, because CY is a radical axis, L lies on the circle with diameter AO prime, so does K, and we're finished. Now, I could have presented this argument to begin with and just given you the solution right away. And I think that I'm pretty sure that's what a bunch of solutions did in their videos. And that's how you would present the solution if you were actually taking the IMO. However, I really think that the solution involving the points K prime and L prime really introduces the motivation for arriving at the solution in the first place. Because after all, it really feels like it's coming out of nowhere. After all, how do we even construct the circumcircle of BYXC or note that its center is very, very special? And again, the answer boils down to using the points K prime and L prime and making observations about them. And this introduces two very important philosophies. So one of them is to always try relating concepts or conditions to ones you know already. In this case, the red angles being equal reminded us of cyclic quadrilaterals. And the second one is that we want to try using power of a point whenever possible, and power of a point always works out when we have all the points that we want are on two tame lines. So number one here is angles cyclic quadrilaterals, which is relate the concepts to ones you know already. And then number two here is using power of a point when the lines are tamed. So these are two very small lessons. But really, the third lesson is the most important one I want you to take from this. And it is consider equivalent points. What do I mean by equivalent? Well, the points K and K prime here, they're basically equivalent if you think about it, because both lie on the circumcircle of YMC and also the line BX. So the problem shouldn't really change when we replace K prime with K or vice versa. And this really helped us when finding our solution. So equivalent points help us find motivation and exploit symmetry further. And that's the main lesson I want you to take away from this problem. Exploit the symmetry and consider equivalent points. If you find a point can have more than one location and it just has a weird configuration issue, then that's something to be very wary of, because you have two possible points and that could possibly lead to a solution. And last but not least, we have the idea that you can draw the diagram as you go. Originally, the diagram was very, very off because this resembles our original diagram a bit, and the green angles here were completely off. But as we did the problem and learned more information, we can make the diagram more and more accurate. And by the end of the problem, we were able to understand the problem statement and the configuration well enough that we could draw a very, very good diagram, or a very decent one, so to say. Like, for example, we can draw in the circle AKL very, very well because we now know that it passes through the midpoints of BY and CX. And similarly, we can also construct the circle KCYM because it passes through K and K prime. Okay, so these are the 4 lessons you want to take away. And the ones I want you to remember are this one and this one. These are more general philosophies that I want you to remember in future problems. The first 2 are rather specific to this problem in a way. So thank you so much for watching this video. Please subscribe if you want to see more.